thank you again, Anna, for inviting me here and organizing this very great symposium. Reading through the brochure here, I was struck by what a distinguished history the University of Calcutta has as the first medical college in Asia, and also the first school of that was for women. So many honors here. This morning, I'd like to go through some of the research that we've been doing, and also summarize other people looking at what we call airway remodeling in asthma, and some of the new approaches that are being looked at in order to see if we can interrupt this process that leads to loss of lung function. So an alternative approach than what we had done with Dr. Banerjee, looking at stem cells as a reparative mechanism. This is looking at some of the basic immune mechanisms, if we can interrupt them at the molecular level. So looking at the natural course of asthma, when a child is born from an atopic family where the parents have asthma or siblings, there's a high risk that they themselves will develop this. And there are two hypothetical courses that can occur. Asthma could develop into a chronic stage right from the beginning of life, and you don't have much chance to interrupt it. Or alternatively, there could be some key factors that we try to identify that if you block them early, you may be able to interrupt the course. And further on, there may be other factors that lead to it being perpetuated, and perhaps if you can block it at a later phase, you can revert the course back such the individual wouldn't have asthma. The big failure of our field analogy is that corticosteroids do not cause a major effect on the natural progression to this chronic loss of lung function. So this is what's seen here. Normal individuals, as we age, we do lose our vital capacity in our airways, but asthmatics are bombarded with a variety of things that they don't handle as well as the non-asthmatic. So air pollution, viral infections lead to what is called an exacerbation, where there's a rapid loss of lung function. They may end up requiring hospitalization or a visit to the emergency department. And what's bad about this is that they don't, once they get over the viral infection that led to a loss of lung function, they don't get back to where they were. So they have an accelerated course, and this can lead to problems later on in life. The major things that is noted in asthma is this intense inflammation of the airways by, in particular, eosinophils, this key mediator of allergic diseases, such that the airways get thickened. You get an increase in the smooth muscle layer that surrounds them that leads to what we call airway hyperresponsiveness. So things like pollutants, allergens, cat, dog, pollen exposure lead to a heightened response. So the airways become more constricted and less airflow, less oxygen getting to their throughout the circulation. And the other one that where the people actually die from asthma is a rapid increase in mucus secretion, so that their airways are impacted, they're totally filled up with mucus glycoproteins, and therefore that's another major problem for gas exchange. So as I mentioned, the eosinophil is thought to be the key player in allergic inflammation, both hay fever, drug allergy, hives, and in particular asthma. And what we know here, that the main player here is what we call this CD4 positive T helper cell, which releases a key set of cytokines called the Th2 group of cytokines. Those are the ones that orchestrate the reaction. And more recently, there's been another group of cells that produce similar proteins. These are the innate lymphoid cells, type 2. So we both have adaptive immune system in the Th2 cells and also the innate immune system that are implicated in the pathogenesis. So looking at the Th2 cells, the key cytokine here for the eosinophil is IL-5. It leads to growth and differentiation of eosinophils in the bone marrow. It increases the expression of adhesion proteins on the vascular endothelium that leads to their migration from the bone marrow into the circulation and then into the lungs if there's an insult in the airway. So the eosinophils get in there. Once they're there, they have a lot of toxic enzymes that they can release. Proteases, oxidative enzymes such as eosinophil peroxidase, and major basic protein that cause tissue injury, leading to that thickening of the airway. And as I'll be describing, they also are very potent producers of these 5-lipoxygenase products of arachidonic acid metabolism, the cysteine leukotrienes, leukotrienes C and D, that also cause the mucus changes in the airways, so that normally goblet cells are less than 1% of the airway epithelium. They become a predominant cell after this process. And the cysteine leukotrienes are very key players there. The other factors that occur are interleukins 4 and 13, and now as subsequent slides, IL-4 we primarily think is leading to IgE formation, the major mediator of allergic processes in people. And IL-13 is the other one that leads to airway fibrosis. It causes a change in the airway epithelium so they become more like mesenchymal cells. Myofibroblasts form and you get excess collagen formation that also lead to this thickening. And they're also the predominant cytokine leading to airway hyperresponsiveness, this bronchial hyperreactivity. So because of that, there's a lot of points of intervention here, and people have been looking at where can we block in these different pathways to make a major impact in asthma. So as I mentioned, corticosteroids have not do anything for this irrevocable decline in lung function that asthmatics experience. And we don't have enough time to go into that today, but most of the big pharma are looking at blockers of the Th2 cytokines, IL-4, IL-13, monoclonal antibodies, or blocking their receptors, or the key expression molecules that lead to this, such as TSLP or CRTH2, that are also key markers of Th2 cytokine function. The area that, for most of my research career, I've been involved in has been in the leukotriene pathway. This is a summary, a review article that we published a few years ago in the New England Journal of Medicine. This is the molecule that was known for 100 years as the slow-reacting substance of anaphylaxis. In a guinea pig models, if you, by just basic pharmacology studies, it showed an intense contraction of the airway smooth muscle in biologic assays. And it was only until the 1980s that it was uncovered what the molecule was. Turns out these are products of arachidonic acid metabolism via the 5-lipoxygenase pathway. One group of molecules is leukotriene B4, which is primarily known as a chemoattractant for neutrophils and monocytes. The ones most closely associated with asthma, though, is leukotriene C4, and then its breakdown products, which are just as biologically active, the leukotriene D4 and E4. They have specific receptors. We're learning a whole lot more about this in the recent years. I was involved in some of the drug development that led to Xylutin, which is a 5-lipoxygenase inhibitor that blocks all the leukotrienes, or the receptor antagonists such as montelukast, which blocks the high affinity receptor for leukotrienes C4 and D4. Where this is important is that the leukotrienes were shown to have many of the in vitro activities that appear to be important in the pathogenesis of asthma. They lead to influx of eosinophils into airways if you challenge an asthmatic with a bronchial challenge and instill into the airways leukotrienes. C4D4, you get eosinophils coming into the airway fluid that you can determine if you do a bronchial lavage. Or similarly, you can do same things in the nose, put a direct droplet of leukotriene, and you can do nasal lavage and see large numbers of eosinophils moving into that tissue compartment. They lead to dendritic cell trafficking. The dendritic cells are key in this Th2 process. As I mentioned, they cause changes in the airway epithelium, leading to mucus production. And they have these key features on the fibroblasts. They can actually lead a fibroblast to transform into a myofibroblast. The myofibroblast is in the airways is the most potent producer of collagen and other extracellular matrix proteins such as fibronectin, laminin, vitronectin. Those all lead to this massive increase in the airway wall size. And they also lead to proliferation and increased contraction of the airway smooth muscle, leading to the airway hyperactivity. So in our work, what got us into this field is we were one of the first laboratories to develop these mouse asthma models to see if we could replicate in mice, because they have such a similar immunology to humans, these features of asthma, and therefore obviously you can do much more manipulations in the mouse than you can in humans. What we did is we inoculated ovalbumin is a classic inducer with an adjuvant, such as alum, to induce a specific IgE response. And we also gave the mice it intranasally to get really intense pathology in the airways. And then in the model, then you, at various points in time, you can intubate the mice, you can get the bronchial lavage, measure in by PCR and other molecular techniques expression of the Th2 cytokines. So in the model, we showed that if you, after a month of this immunization, the airways, here's the airway lumen, nice and open in the saline-treated mice. You can see it's nearly totally occluded with the mucus glycoproteins. And all these blue cells that have moved in here are stained for eosinophils. So at least in the model, it's a pretty good replication of what you see in asthma. This is one of the things when Dr. Banerjee worked in my lab, what brought her into my lab was that she was also working in mouse models looking at vascular endothelium expression of adhesion proteins leading to this trafficking. Now, if you give a 5-lipoxygenase inhibitor to prevent formation of leukotrienes, you can see that these features of asthma are nearly totally inhibited. The airway lumen, you don't get the mucus secretion, and that eosinophil influx into the tissues is also blocked. So, what we'll go through here is this model of remodeling of the airways, mucus hypersecretion, the subepithelial fibrosis, and increase in the muscle layer. And also, another key feature of this remodeling is angiogenesis. I know one of the other speakers here today is involved in been involved in vascular growth in tumor models. So in this model, you get all the good features of asthma, at least for a researcher, all the bad features if you're a patient. Allergen-specific IgE, you get infiltration of the CD4 positive Th2 cytokine producing T cells, as well as other cytotoxic T cells. And you get release into the airway tissues and the secretions of Th2 cytokines, IL-4, 5, 13. You get the goblet cell metaplasia, so the goblet cells increase in number and they also produce much more mucus on a per cell basis than before. And you get the smooth muscle hypertrophy and contractility, leading to fibrosis of the airways. And the bad thing that a mouse would have, and a human even worse, is this key feature of asthma, such that they have markedly contracting airways so that they get into trouble and lose lung function. So the first slide I showed you was a short-term model, and we extended it by giving the mice immunizations over a much longer period, here over nearly a 3-month period. And then we decided we wanted to see, could we actually reverse these established features of asthma? Because our whole goal here is we're faced with patients that developed asthma. We're not in a situation where we're treating babies where we can try to block it at this point. Most of our patients are adolescents, adults. How do we, if they've got changes of airway remodeling, can we revert them back toward normal? And we think this would be a pretty difficult task because, as you can see, these airways are filled with fibrotic proteins, mucus. Can we actually change that? So in that, into the mice, we gave them implanted mini osmotic pumps so they could get long-term delivery over a 3-month period of either steroid, dexamethasone, or the cis-leukotriene receptor antagonist montelukast. So here's what we showed. That when we started the infusions, we wanted to make sure that the mice did have established airway fibrosis. So on day 73, you can see that, looking at H&E stain, dense influx of monocyte macrophages, eosinophils into the lung tissues, mucus hypersecretion in the airways, and this blue stain, trichrome stainness for collagen. So you can appreciate how bad these airways look throughout the mouse lungs. It's at this point that we intervened for a 3-month period in another group of mice to see if we could change that. And in fact, we could. So this is now 3 months later, day 163. 3 months treatment of either saline, a corticosteroid, dexamethasone, or a 5-lipoxygenase blocker, the montelukast. So here again is at now day 163, blue stain, lots of collagen, thickened airway smooth muscle here. And you can see that if 3 months of treatment with montelukast, marked decrease in the blue staining. So actually that is a reversible feature of airway remodeling. By blocking the cis-leukotrienes over that period of time, you actually were able to go back toward the normal structure. The airway smooth muscle also decreased in size. So it's a process that's plastic. You can shut off the hypertrophy and hyperplasia in these processes. And what fit in well with human experience is that corticosteroids didn't affect this process. Here's the steroid-treated group. You can see dense collagen with the blue stain, and the smooth muscle layer was also not changed after the high-dose dexamethasone therapy. So these part of the data showed that airway remodeling is a reversible event if you have the right interventions, and that the cis-leukotriene pathway appears to be a major mediator of the process. Now, the leukotrienes are more of a downstream effector process. Lots of cells, the eosinophils, monocyte macrophages, neutrophils are producing them, and it's kind of late in the game. So a lot of people were looking at trying to intervene earlier in the immunological cascade to see could you have even a better effect if you block something earlier in the disease pathogenesis. So if you look at the immune pathways leading to, in this case we're focusing on allergic lung disease, the main person here is the IgE molecule. That's what makes a atopic individual different from the non-allergic. They're producing these specific IgEs against pollens, decimites, cockroach proteins, dog and cat. So 20% of the population is allergic or atopic. And what happens is that tissue dendritic cells in the lungs encounter the allergens, such as the cat protein. They take it up and they move to the airways. Some of the chemokines lead that processing into the actual lymph nodes in the lungs. The dendritic cells present the antigen to the Th2 CD4 positive T cell in a MHC coupled reaction, very specific. leads to the formation of switching of the B cells to form plasma cells that secrete these allergen-specific IgE molecules. So it's very early in the process. Mast cells and basophils are the major mediator cells of allergic diseases because of their potent chemicals. They contain preformed histamine in their cytoplasmic granules. When they degranulate, they release the leukotrienes and other chemicals. And they have high affinity Fc receptors for the IgE molecule. So in the right situation, when the allergic individual encounters the antigen, the inhalant, the CAT protein, the mast cells of the allergic individual that have that will fire them off and degranulate and release interleukin-5 again, leading to this whole cascade of changes in the mucus glands and the airway smooth muscle that I described in the previous slides. Some exciting area that we won't have time to touch on, but there's a lot of other cells that are impacting this process now. Th17 cells that can lead to more neutrophils coming into the airways in patients with severe asthma. Th9 cells that are very similar to Th2 cells in their what they do. And kind of as a counter-regulatory cell, the T regulatory cell that can shut off this allergic response. So it's a lot going on, but you can see pretty early in this response is the IgE molecule. So a lot of people have been looking at that in order to maybe if we target this early, we're going to have really nice results for our patients. Scientists at Genentech pioneered this approach with the monoclonal antibody, a humanized one against IgE called Omalizumab. The trade name, I'm not sure in India if it's called Th2 or has a different trade name, but it targets part of the constant region in the Fc portion of IgE, the third domain. It's an IgG against the IgE. And the complexes that form lead to a very, within half an hour, lead to a rapid decrease in this free form of IgE in the circulation. So a 90% reduction of IgE in a free form, half an hour after giving it subcutaneously. And I'll show in the next slides it has some big effects on the immune response. I should mention, I think you were in the first lecture, there was a talk of the amphotericin costing $3,000, $2,000 a dose. This one in the US is running around $3,000 a dose. Some people require twice a month, so it could be up to $50,000 a year in healthcare costs. So big problem with getting it to your patients. So by this complex that forms, it's unable to cause mast cell degranulation. It also has another nice bonus effect. It also leads to a downregulation of its receptor on the surface of the mast cells. So the mast cells become much more unable to release their chemical mediators. And this slide just summarizes some of its biologic effects. Decreases free IgE, so you have less cell-bound IgE. The high affinity receptors, it reduces the number. Mediator release goes down. Some of the pivotal studies have shown that it has a major effect in improving the quality of life of the asthma patient. This was a study where they looked at inner city children in the US, so places like Detroit, Baltimore, New York City, where there are large populations, a lot of families living at poverty levels. There's the highest level of asthma in this population. They have more exposure to rodents, mice, rats, cockroaches. Those are all primers of the allergic response. And they showed that if they treated them for a year with the Omalizumab, the Xolair immunizations that are given either twice or once a month, marked decrease compared to the placebo-treated group that were giving their normal anti-asthma medications, bronchodilators, corticosteroids, things like that. Days with symptoms, these exacerbations that occur in the winter and springtime during the pollen season, wintertime during the viral season when children get into trouble, and also adults with asthma. And you can see that was smoothed out. If you remember back to my first slide, the exacerbations are the key thing to prevent, because every time an asthmatic gets an exacerbation, they fall off their curve, so they have more rapid decline in lung function. So you really want to prevent that. And their inhaled corticosteroid dosing was also decreased. This is important in the pediatric population, because when you have to treat the patients, children with high-dose steroids, it impacts their growth, so they can have a decreased stature. So in our study, what I'll be showing now will mimic a lot of what I've just shown you, what we did with the anti-leukotriene approach. We wanted to see if we blocked IgE in the mouse, would we have similar effects? Could we reverse established features of airway remodeling? And then we didn't know if we could do that with that, but if we were, we harvested all the lungs in order to obtain their RNA, so we could do genetic analyses, molecular analyses looking at mRNA and also microRNA changes. So similar to what I described before in the leukotriene model, we gave them ovalbumin over a 3-month period to establish the airway remodeling, smooth muscle increases, fibrosis. And then we treated them with a anti-mouse IgE, and so it was an IgG from the rat, and then gave them an isotype control over, as you can see, a long treatment period, close to 100 days. See if we could give them a good chance to see if we could reverse these changes. So one of the first things that we noted was in the group with the dark, this is looking at airway hyperresponsiveness. You put the mouse into it's called a mouse platysmograph or a body box, similar but just on a smaller scale than what you would do in a human. And you give them increasing concentrations of methacholine as a non-specific irritant. And an asthmatic individual will have a bigger fall in their lung function, inhaling the same concentration dose compared to a patient without the airway hyperresponsiveness. And we showed that compared to the treatment group, OVA treated versus saline, the saline here don't have much of a change in their airway responsiveness with increasing doses of methacholine. Highest group is seen with the OVA-treated mice. You can see that we got about a 50% reduction if we gave them anti-IgE for a 3-month period after development of this airway hyperresponsiveness. So that aspect was partially reversible with this intervention. We also showed that the anti-IgE, as I showed you before, compared to the control group treated with OVA, but only receiving saline for a 3-month period, you can see that the blue stain is markedly decreased. The airway smooth muscle was also decreased. There again, it was about a 50% reduction by this intervention with anti-IgE. You can see a pretty nice resolution of their airway inflammation to this eosinophil monocyte macrophage influx by this. So these, this part of the study showed that it was very interesting and promising that this may be actually impacting these major pathophysiologic features of asthma. And here again too, there was a significant reduction in, if you measure collagen by hydroxyproline content in the lung tissue by anti-IgE compared to those that were treated with the isotype-specific control. Now, one of the main features, I'm sure Dr. Banerjee's in her lectures has highlighted this key feature of airway fibrosis in patients with not only asthma, but with idiopathic pulmonary fibrosis. They get what's called an epithelial-mesenchymal transition. It's a recapitulation in reverse of what's normally happening in embryology. So the established airway epithelial cells become dedifferentiated toward mesenchymal type cells. And these mesenchymal cells are the ones that are producing collagen.